Hi, in this video, I will be showing you problem number 21 of chapter 16, section 7. Evaluate the surface integral, double integral over S, f dot ds for the given vector field f and the oriented surface S. In other words, find the flux of f across S. For closed surfaces, use the positive outward orientation. F of x, y, z equal to z e to the xy I minus 3z e to the xy j plus xy k. S is the parallelogram with parametric equations x equal to u plus v, y equal to u minus v, and z equal to 1 plus 2u plus v, where u runs from 0 through 2 and v lies from 0 through 1. So here, main thing is to find out the surface integral of the vector field, which is also known as the flux across the surface. And S is the oriented surface. In the oriented surface, the positive outward orientation is considered to be, positive outward normal is considered to be the positive orientation. So we'll see what an oriented surface means and what is this formula, integral over S, f dot ds, which is the surface integral for a vector field. In the earlier problem, we saw surface integral for a scalar field. Now we are going to do this problem for a vector field. So the formula is slightly modified. So what is an oriented surface? Give an example of a non-orientable surface. An oriented surface S is one for which we can choose a unit normal vector n at every point so that n varies continuously over S. The choice of n provides S with an orientation. Two sides for an oriented surface and one side only for a non-oriented surface. Keep in mind. Okay? There are two possible orientations for any orientable surface as shown below. So, one is pointing outward. Those are positive orientations. One is pointing inward. So, these two normals are opposites of each other. So, if n1 and n2 are considered a unit normal vectors for an orientable surface, n2 is negative of n1, as shown in this figure. A Mobius strip is considered to be a non-orientable surface which has only one vector n. Now let's see what the formula is about. Define the surface integral or flux of a vector field f over an oriented surface S with unit normal n. So this is double integral over S f dot ds, which is equal to double integral over S f dot n ds, where n is the unit normal vector. The surface integral is also called flux of f across the surface S. How do you evaluate the surface integral S if S is a parametric surface given by a vector function R of uv? That is double integral over S f dot ds equal to double integral over d f dot RU cross RV dA, where D is the parametric domain. And we multiply by -1 if the opposite orientation of S is desired. Now let's write R of uv in our problem, which is xi plus yj plus zk, where x is given by u plus v, y is given by u minus v, and z is given by 1 plus 2u plus v, with the restriction of u lying from 0 to 2 and v lying from 0 through 1. So R of uv, if you substitute the values of x, y and z here, we are going to get an expression like that: u plus v times I plus u minus v times j plus 1 plus 2u plus v times k. U runs from 0 through 2 and v runs from 0 through 1. We'll call that as equation 1 or step 1. R sub u, which is partial derivative of r with respect to u, is 1i plus 1j plus 2k. We'll call that as step 2. R sub v is 1i minus 1j plus 1k. We'll call it step 3. Now we'll get the cross product, which is determinant I, j, k on the first row. Second row are the components of R sub u. And third row are the components of R sub v. So which is I times 1 plus 2 plus j times 1 plus k times -2. So we get 3i plus j minus 2k. We'll call it step number 4. So RU cross RV is done. Next, substituting for x, y, z in f, we get f of r of uv would be a big expression, because every x and y and z in f must be replaced by the parametric representation for x, y and z in terms of u and v. So we get all of this. 1 plus 2u plus v times e to the exponent u plus v times u minus vi minus 3 times 1 plus 2u plus v e to the exponent u plus v times u minus vj plus u plus v times u minus v k. So we get f of r of uv equal to 1 plus 2u plus v e to the exponent u square minus v square I minus 3 times 1 plus 2u plus v e to the exponent u square minus v square j, then u square minus v square times k. We'll call it step A. R sub u cross R sub v, we already found out. That would be 3i plus j minus 2k from step 4. So we have to take the dot product of these two now for the integrand. So the problem says that the positive orientation means outward normal. Positive orientation must be used. But if you notice RU cross RV, which gives the normal to the surface, which has a negative z component. In order to make it positive, we have to change the sign there. So Ru cross Rv has a negative z component. We will use negative of Ru cross Rv in the formula to make it positive orientation for upward orientation. So double integral over S f dot ds, vector f dot vector ds, equal to double integral over d vector f dot negative Ru cross Rv dA. So we'll call it step P. So it is integral 0 to 1, integral 0 to 2. So integral 0 to 2 is for u, integral 0 to 1 is for v. Which is negative 3. So if you dot product f with negative of Ru cross Rv, here we are actually taking the negative of each of the values here, each of this, because we are taking the negative orientation of that. So it is negative 3. When we take the dot product, we would multiply the components of f by negative of each of this in Ru cross Rv. So it is negative 3 times 1 plus 2u plus v times e to the exponent u square minus v square plus 3 times 1 plus 2u plus v e to the exponent u square minus v square plus 2 u square minus v square du dv. So it's an integral 0 to 1, integral 0 to 2. So the first two terms cancel out. So you get 2 times u square minus v square du dv. So if you evaluate that, it's 2 times integrating with respect to u. So u cube over 3 minus u v square dv. Of course, we have to substitute the limit 0 and 2. So if you do all the computation of this definite integral, we arrive at two times 8 over 3v minus 2v cube over 3 between 0 and 1, which is 2 times 8 over 3 minus 2 over 3, which is 2 times 2, 4. So here mainly we have to remember what formula we are using for a vector field, surface integral of a vector field, so which is f dot Ru cross Rv. But keep in mind, when the problem says that positive orientation is outward unit normal, then you have to remember to make the orientation positive by taking the appropriate unit normal vector. Hope this video helps.